Hi, everybody out there in podcast land. This is Mr. Folly, and welcome to AP Podcast 14.2, which I'm sure hoping will get up on time. 14.1 is up online in case you wanted to hear it again from class. Today we're going to do percent ionization, polyprotic acids. Poly means many, protic means H positive. And H positive is a proton because H has one electron and only one electron. And H positive means you remove it, so you just have H with a plus 1. And we're going to look at the K's of those things. Kb, which is just like Ka, which is just like Kc, only it's for a base. Kw, which is just like Ka, which is just like Kc, which is just like Kb, only it's for water. And then there's the equation relating Ka to Kb is Kw. Multiple OHs are all strong, meaning that they all come off. And remember, polyprotic acids come off. H2SO4 would be 1H at a time. Ranking acid bases by the strength, acid-base strength by conjugates is the last thing we'll do. So percent ionization can be found by simply taking the amount ionized dissolved over the starting amount. So if I'm given a cheesy reaction, I tell you I have 2 molar of it, and you find out that you're given, I don't know, say the pH or something like that, and somehow or another you know the H3O positive. What you would do is, once you know the part, and you would only take one part, not both, not 0.006, but 0.003, divided by your starting amount. Okay. I prefer to call this the minus x. Okay, because if you have all these things, just 1x, so minus 1x is the amount that dissolves. Okay. To do that, so let's do an example or two. Here's a bunch of them. A solution of 2 molar weak acid is 0.52% ionized. Find Ka. So I'm just going to call it HA plus H2O. Equilibrium with H3O positive plus A negative. It's a 2 molar. And 0, 0. If it's 0.52% ionized, what that means is I'm going to have 2, and 0.52% of it will ionize. Now, this is not 0.52. It would be 2 times 0.0052. Remember to move the decimal place 2 spots, and that will give it to you. So 2 times 0.0052 is 0.0104. So that means minus 0.0104. Remember your percent ionization, this year, minus x, plus 0.0104 plus 0.0104. And then I can get Ka from this. So at equilibrium, I have 2 minus 0.0, so 2 minus answer 1.99. 0.0104, 0.0104. So Ka is going to be 0.0104 squared over 1.99 divided by 1.99. And again, I'm using my equilibrium concentrations. I know mathematically the answer is not going to be any different, but you want to use your equilibrium concentrations when you're solving for K. 5.44 E negative 5. And there you go. 54. 0.4 molar solution of hypochlorous acid HClO. The Ka is blah, determine the percent association. So ice diagrams are your friend. Point 0.4 molar. 0, 0, minus x plus x plus x, 0.4 minus x. What did it tell us? Oh, we know Ka. X and x. So I gotta write my Ka expression. 3.5 E negative 8 equals x squared over 0.4 minus x. Welcome to the world of the solver. I love the solver. So this is what I'm putting in my calculator, but I'm not writing it down. Well, first I'm going to my math. 0. Moving on up. Clear that out. Quantity x squared divided by quantity 0.4 minus X, quantity minus 3.5 E negative 8. My guess is 0.00001. Why not? Alpha enter. And I got, if I'm an idiot, I got 1.18. Alright, it says 1.18, but I know that's a nonsense answer. And then I scroll all the way to the right, and I see it's E negative 4 is X. So this is X. So if I want to find the percent dissociation, what I would do is 1.18 E negative 4 over 0.4 minus 1.18 E negative 4, which I wouldn't have really put that in there anyway because that's still 4.00, that many sig figs, times 100% equals 1.18 E negative 4 divided by 4, 2.95 E negative 5. Come on, baby. Oh, what did I do wrong? If that's X, it should be X divided by 0.4. 1.18 E negative 4 divided by 0.4. Well, here's your chance to get extra credit. Figure out what I did mathematically that's wrong on that, and put that on your pod quiz tomorrow. Sorry about that. Polyprotic acid, multiple H acids. The first K is large as compared to the following. So notice this is 10 to the negative third. This is 5 powers of 10 less. So that's 10. 1, 2, 3, 4. No, I guess it is 100,000 times less, isn't it? Oh, well. And then this is another 5 powers of 10 less. So imagine if someone gives you $1 million and someone gives you 100,000 times less than that. It would be insignificant in most cases. Now, if what you're worried about would be the amount of HPO4 negative 2 or some of the other ions that come on, it becomes significant because this is significant compared to 0. But if you're talking about something being 5 powers of 10 less, then like the H's that you add, this will add 100,000 times less H's. So let's pretend this adds 1 H positive. Well, this would add 100,000th of an H. Yeah. And this would add 100,000th of 100,000th of an H. So the ones don't matter much. Find the pH and concentration of all species in 5 molar H3PO4, and I gave the K's up here. So I'm going to have to bounce back and forth to get the K's as I go through this, and this is a long problem. Leave a lot of space in your notebook for it. So H3PO4, I'm going to drop the water out of this just because I'm being lazy. Makes H3O positive plus H2PO4 negative. I've got 5 molar, 0, 0. Minus X plus X plus X. So 5 minus X, X, and X. My Ka was 7.5 E negative 3. So 7.5 E negative 3 equals X squared over 5 minus X. Solverland, X equals. Okay, so solver. Where'd it go? Math, 0. Equation. Hopefully I'll do a little better this time. X squared divided by quantity 5 minus X quantity minus 7.5 E negative 3. My guess would be 0.0001. And I got 1 E negative 4. Well, that's pretty nice. X equals 1 E negative 4. So that means that that equals H3O positive. It equals H2PO4 negative right now. And H3PO4 would be 5 minus 1 E negative 4, so that's still 5. Throw a little molar in here. H3PO4 because 5 minus 0.0004 is still 5. Okay, now what I have to do is figure out, I have to associate H2PO4. Oops, negative. Yield positive, whoops, plus HPO4 negative. My concentration for H2PO4 I'm starting with is right here, 1E negative 4, 0, 0, minus X plus X plus X, 1E negative 4, minus X, X, and X. So my K for that is 6.2 E negative 8 equals X squared over 1 E negative 4 minus X. Solver time. Oh good, I still have my solver up here. X squared divided by 1 E, whoops, that's a comma, 1 E negative 4 minus X, parentheses, parentheses, minus 6.2 E negative 8. And my guess is 1 E negative 4, sure, why not? Solve it. Error divided by 0. Let me do this again, and what I get actually should be 6.2 E negative 8, because I know a shortcut. So X equals 6.2 E negative 8. So that means that 6.2 E negative 8 is the added H3O positive concentration. Well, notice if I have E negative 4, if I have E negative 4 concentration, I'm adding E negative 8. I'm adding nothing important. If I have, I am also, but I did make, where am I? I did make that much HPO4 negative. And I did subtract E negative 8 from H2PO4, but E negative 8 from E negative 4 will be insignificant. So, okay, so I've added one thing. And that's it. I'd have to do this again to get my phosphate amount. So here we go. So I have HPO4 negative 2 plus H2O. I don't know why I put it in this time and I didn't before. Gives H3O positive plus PO4 negative 2, negative 3. And this was 6 point, oh, I forgot. I'll need all these. 6.2 E negative 8 and 4.8 E negative 13. Okay. Oops, you know what? I forgot. Oh, darn it, I forgot something, which I hate. This right here should not have been X. My starting value here is not X. My starting value here is 1 E negative 4. I'm so sorry. I'm going to add X, and then at equilibrium I have 1 E negative 4 plus X. So, sorry. So I'm going to rewrite this, and I'm going to rewrite it in a different color. We'll go black. So I should have 6.2 E negative 8 equals 1 E negative 4 plus X times X over 1 E negative 4 minus X. My answer will turn out to be X equals 6.2 E negative 8. It's always equals Ka2 when you do this. Because if you look, the X value is very small. Before I talked about how it's insignificant. So basically what happens is mathematically these two turn into 0, so that 1 E negative 4 on the top and the bottom will cancel, and X will equal 6.2 E negative 8. Really sorry about that. Please forgive me. Please forgive me. Be sure to mark it down for your extra credit point. And then I just forgot what H3O positive was. 1 E negative 4. 1 E negative 4, and phosphate is 0 initially. Minus X plus X plus X 6.2 e negative 8 minus x, 1 e negative 4 plus x, and x. So again, relative to 0, this x is significant for phosphate. Relative to 1 e negative 4, this x is not significant. But my K was 4.2 e negative 13 equals 1 e negative 4 plus x times x over 6.2 e negative 8 minus x. Solver. X equals. Ooh, doggies, this looks ugly. And I'm going to pretend to do it because I know the answer because I'm cheating. So you won't hear me say my usual walkthrough. Long pause, sorry about that. I got 2.6 e negative 16. I hope that's right, molar. And that would be the concentration of phosphate only. Again, yes, it's true that this is added to your acid amount, but if you're adding 10 to the negative 16th when you already have 1 e negative 4, you're not adding anything significant. Let's move along. Calculate the pH of the following aqueous solution. pKa1 equals 7. Okay, this I just put in here because I wanted to show you what pKa's are. pH is negative log of H. pOH is negative log of OH. pKa is negative log of K. So this one has 2. Ka1 would be the first hydrogen leaving, and this would be the second hydrogen leaving. So let's figure out what these K's are going to be. So 10 to the negative 7 is pKa1. And 10 to the negative 12.89, I'm going to put that in a form I like better. Second log 12.89, oops, negative 12.89 is 1.29 e negative 13. Do you see how these two are going to be a difference of 6 powers of 10 away from each other, so a million times different? So that means the second K is not relevant. So all I'm going to do is the first K and be done with it. So H2S, again shortcutting it, H3O positive because we're already here forever, S negative 2, so 0.57, 0, 0, minus X plus X plus X, 0.57 minus X, 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 1 e negative 7, which is from here. Ka1 is what I'm using. I'm ignoring Ka2 because its contribution is negligible. X squared over 0.57 minus X. Solver it. And as you solver it, you get X equals 2.39 e negative 4. All right, moving on. So second and third associations are insignificant. Yay, sig figs. The 5% rule is when you can drop it. Okay, you don't need to worry about that. The following question refers to a solution that contains 1.42 molar hydrofluoric acid and 3 molar hydrocyanic acid. Oh, I thought I changed this. Okay, so we're looking at the effect of Ka. So what is the pH of this mixture of weak acids? So looking at this, notice how HF has a Ka of 10 to the negative 4. HCN has a K of 10 to the negative 10. You're talking about 6 powers of 10 difference, meaning HCN is not important when determining the pH. So that means we're going to do a quick ice diet. Well, I'm going to do Ka equals X squared over HA. I'll show you how this, no, I'll do a quick ice diagram. Where am I? HF, H positive, H3O positive, plus F negative. And then I would have 1.42, 0, 0, and at equilibrium. I think you won't mind if I drop my change part out of it. We'll need that again later. Oops, minus X. But that's good to learn before. So 7.2 e negative 4 equals X squared over 1.42 minus X. solve for x, and plugging it into my calculator. I got 0.03197. So if I want the pH of that, that equals H positive, by the way. So pH is negative log 0.0320, negative log, second answer, and I got 1.50. B. Bad news is this is getting long. Good news is I'm doing your homework. 0.27 mole sample of a diprotic acid, H2A, was dissolved in 250 milliliters of water. K1 is 10 to the negative 5. K2 is 10 to the negative 10. Calculate the concentration of A negative 2. This is nice. It's 1E negative 10. Remember, the concentration of the second ion there, what was that? No, the concentration of A negative. Oh, concentration of A negative. Oh, no, it's not. That's A negative 2. So the concentration of A negative 2 is always equal to Ka2 from what we did before and did that H3PO4 problem. Yay. A pH of a solution of this guy right here is blah, 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 blah. Now, this is 4 powers of 10. Am I worried about that? 10,000 times difference? Not worried about it. Goodbye. So all I'm going to do is run that through like normal. And I'm going to skip that because I want you guys to be done soon. Which the following 0.1 mole diprotic acid with a second dissociation affect pH significantly? This is 5 powers of 10. This is 4 powers of 10. This is 5 powers of 10. This is 1 power of 10. Woo! That would be D. Remember, pH is, you want to look at pH of XX. This would be 1 power of 10. This would be 2 powers of 10. That's the way pH works. It's a logarithmic function based on the powers of 10. If you don't understand that, go smack your math teacher. Kb is exactly the same as Ka, but focuses on the base part. Almost always has an NH2 on the end in this class. It rarely has an OH because these are weak bases. So if I were to write the Kb expression for this, Kb equals CH3 NH3 positive times OH negative over CH3 NH2. And that's your Kb expression. Here we go. pH of a 3-point molar solution of aniline, and they give you the Kb. Notice it ends in an NH2. So C6H5NH2. I will show the water here because the hydrogen's got to come from somewhere. So water's acting like an acid in this situation, so it's giving an H. C6H5NH3 positive, and notice that nitrogen that takes it. Lone pair, grabbing that one, plus OH negative. 3.8, 0, 0, equilibrium. I'm jumping right down to that. 3.8 minus X, 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 3.8 E negative 10 equals X squared over 3.8 minus X. Solving. And then, let's see here. X equals 3.8 E negative 5. And that's molar of hydroxide. So there's 2 ways I can get pH from this. One is using H positive times OH negative equals 1 E negative 14. I think I forgot to put that on your equation list, so put that in there if you didn't. I'm not going to use that. I'm going to find the POH first. So negative log of 3.8 E negative 5 equals POH. So negative log, answer is 4.42, which makes sense. It's less than 7. POH is less than 7 for a base. So then my pH, 14 minus 9.58. Yay. I'm skipping some of the problems I intended to do. Oh, man. Oh, what is the pH of point solution sodium fluoride? Okay. You know what? This is long enough. 25 minutes. We'll have to finish it in class. I just can't do it to you anymore. See you guys.